or good evening, and welcome to this last day of our workshop. It's been really a very interesting and stimulating week, I think, and today will be no different. We have 3 excellent talks on a variety of topics, all of which are connected indeed by the challenge that they face through this inverse problem, which we've been discussing in our workshop. So to start us off this morning, we're really very happy to welcome Kei-Fei Liu. So many of you, of course, will know Kei-Fei and his wide variety of interests in theoretical physics and in lattice QCD in particular. So Kei-Fei, it's a real pleasure, and thank you for joining us this morning. So Kei-Fei will talk about the inverse problem in neutrino nucleon scattering and the, well, famous or infamous, I suppose, depending on how you think about it, Roper state.
Still is, yes, the status, yes. Yeah, thank you for having me. It's my pleasure to share all these puzzles and challenges with you. As Sinead said, we'll have neutrinos, nucleon scattering, and the Roper state as examples of the inverse problems. I'll talk about lepton nucleon scattering via hadronic tensor and as inverse problem, and the Roper puzzle, particularly it's the Fermi action dependence and a variational. We'll show you the variational calculations and basin reconstruction approach. It's not somehow.
Can you click with your mouse? We had this a few times that the keys don't work.
Right.
In Zoom.
Yes, there you go.
Ah, perfect.
Yeah, right. Thank you. Yeah, thank you for the solution here. It's already a challenge. Okay, in the neutrino in the lepton nucleon scattering in general, the cross section is a product of a lepton and the hadronic tensor. The hadronic tensor. Can you see my cursor? Okay. It's a current correlator in the nucleon in this case, and that is you can see it's a spectral weight of the sort of matrix element squared, and then the delta function in space time. However, on the lattice, we're working in Euclidean space. We can construct 3 momentum conservation laws, but not the energies. We only have exponential in time. So in that case, we can first define in the Euclidean path integral a current correlator in the nucleon, which you can divide it the legs or truncated legs with a 2-point function. But that will be just a momentum transfer in spatial directions. All right, hold on. Let me see if I can do that. Now, so for the, of course, it's an important problem for neutrino nucleon scattering nowadays. Basically, the cross-section is not known or not well known. People have in the experimental high energy efforts in the US especially is like a Dune experimental facility, and then their energy will be from 0 to 7 GeV neutrino energy, but people don't know this cross action. Therefore, all these experiments, neutrino oscillations, CP violations, all these things will be quite uncertain. Therefore, one needs some fairly precise, at this stage, neutrino nucleus scattering cross action. But the next stage, if one can use the nucleon as a target, the neutrino nucleon scattering will be important. Then there are several regions. So you can see this is an elastic region, but in the nucleus it's been smeared off, becomes elastic form factor. It's not a sharp peak, but it's quasi-elastic, they say. And there are resonance regions and nucleus scatterings. And there's a region called shallow inelastic scattering. And before the deep inelastic scattering, and they can break up into various regions. Therefore, spectral decomposition is important, being able to isolate all these pieces of contributions. Now, for the hadronic, as I said, tensor in Euclidean space, as I said, we integrate only the three momentums, and the current correlator will have exponential terms. Therefore, one cannot go back to Minkowski space by simply taking the inverse Laplace transform. Instead, one can look at the Laplace transform expressions, in other words, and consider that as an inverse problem. In other words, what you measured here is in Euclidean space with a function of tau. Then if the kernel for this folding of integration, and this is what we really want in the momentum transfer. As I can see, experimentally, the photon proton total elastic scattering has elastic and all these regions. I can see that's fairly flat in the deep elastic region from 5, 6, 7 GeV and up. So this is the challenge that we want, what we face. Now, of course, the inverse problems is ubiquitous, as shown, I'm sure, by this workshops. And here is a sort of a Laplace transform with exponential factors. And there are, for example, experimentally, when you extract the PDFs from experiments, that's the inverse problem, where you have a Wilson coefficient, coefficient functions, but that is folded with the PDF that you really want, and this is related to the experimental form factors and so on, structure functions. And of course, it's a quasi-PDF and cross-actions, pseudo-PDF, and so on and so forth, which I'm sure that people have talked about before. Now, so there are several methods that we have tried. One is a Backus-Gilbert method, maximum entropy, and basin reconstructions. That's the basin reconstruction approach. I won't give you the details. I'm sure you have heard more before. So this is the case that we'll discuss more later. That is considered a nucleon and Roper state. Actually, it's a nucleon correlator on the 48 lattice, 48 cube lattice. The lattice spacing is 0.114 Fermi and physical biomass. Right. So you can see that when you look at Backus-Gilbert, it is sort of could not resolve these two structures. Looks like the nucleon and the Roper, but it's also a broad structure here, as probably people have realized is good for a broad or more uniform distributions. Maximum entropy, which one is it? Okay, maximum entropy is the hiding myself. It's the orange one, which is doing reasonably well. But basin reconstruction particularly likes sharp peaks, so you can give it much sharper peaks and so on. I will come back to that later on. Now, we also tested, because of the structure that we have seen here, there are elastic scattering and maybe inelastic pi and pi, before it goes to the more sort of uniform deep elastic regions. So we just tried it one peak and one sort of uniform distributions. As you can see that, again, Backus-Gilbert couldn't resolve this, the peak here, just give a broad distribution. The maximum entropy is the orange one, which is doing reasonably well. Basin reconstruction, the version that we implemented from Alexander has some sort of a slight oscillations, as we can we see here. Okay, and presumably that can be improved also. Now, there are cases that we tested the hadronic tensor by looking at the elastic scattering. Elastic scattering, there's no energy transfer, and that state in between the currents, 4-point divided with 2-point functions, the lowest state is the elastic scattering when you have q squared equal to 0. That one does not need to do the inverse problem. So you can just fit it, right? Just like fitting any ground state of two-point functions. So yeah, four-point functions basically has the same structure as a two-point functions. And then you can see this is the case. We look at the charge current in this case, and that charge current particularly will be for elastic scattering is the electric form factor squared. And so you can see that for the charge current, when you have a zero momentum transfer, it's just charge, and then charge for the proton is 2, and square of that is 4. So you can see that it's coming from various combinations of that, and these are different form factors. And this is on the right is a test how this thing does. So we calculate a 4-point function, get their sort of momentum transfer for the structure function, and then we also calculated the 3-point function directly for the U and D quarks. And so when we have the 4-point function, we take a square root of that, give you the electric form factor. You can see that basically they match up, you know, within errors. This one for the different form factors, they seem to match up. So that's a test that indeed that we didn't do anything drastically wrong with the 4-point functions. Okay. All right. Of course, for the neutrino scattering, you have a V minus A current, then it's also various combination of form factors for elastic scattering, electric, magnetic, you know, and axial, and so on and so forth. So for the elastic scattering, people can use the 3-point function calculation and get the elastic part. but we are interested in things beyond that. It's not just elastic. You have a neutrino energy, at least for the Dune experiment, we need to cover at least 0 to 7 GeV. So this is a test for the beyond elastic scattering for a particular case that we just looked at with a momentum transfer unit squared 1, 2, 3. And that's the 4-point function divided by 2-point functions. And when we do the Basin reconstruction, you can see for different energies and momentum transfer, so far we only see one peak. We don't see many structures for the particular lattice we have. This lattice, the quark mass, the pion mass is about 400 MeV. It's pretty heavy, and we don't really precisely know what that structure is. Perhaps just Roper, okay, and so on. Now, for the case that we want to look at, you know, going into the large momentum transfer, the early one we get, you know, momentum transfer, which is 2 pi L, and that's probably 1 or 2 or 3 units. Here, if we want to go to large momentum transfer, and this unit, for example, is 3.57 in this case, and the proton we put, in order to get a large momentum transfer, you need to move the proton with such a speed. So 0, 3, 3 components, and Q it can get to very large. We know it's hard to move the nucleon at very large momentum because it's noisy, but Q for some reason you can go to fairly large, like in this case -6. And still we just see basically just one structure. Okay? So at large Q squared, and then the elastic ones and the Roper, those resonances are dropped off because you usually have a dipole form factor, but this is squared, so it's a quadruple form factor. Get the Q equal to 2 GeV or so, and then you get very large suppression. However, the M pi is not suppressed, so this is likely to be the M pi and so on, but we need much further study of this and much more data and so on. But unfortunately, again, we see one structure and not more. In particularly, when we look at the different actions and different lattice spacings, this is lattice spacing limited. We sort of look at the effective mass at very short time separation and learned that in order to, if you want to go beyond the low-lying states, beyond 7 GeV to look at the deep inelastic scattering, you will need a lot of spacing to be 0.02 or 0.03 Fermi. So it's very, very challenging, and you need a large lattice for that if you want a small quark mass.
Sorry,
Yeah.
your lattice seems to be very long in the time direction.
Oh, sorry.
Are you using anisotropy?
Anisotropic ones, yes.
Right.
We took one of the Clover, yes, 24 cube times, oh, sorry. How do I go back? Yeah, times 120. It's one of the JLab's anisotropic lattice. Because we wanted many, many points, right? In an inverse problems, you want many points in the time resolution, and that's what we got. Still, we get only one state in this.
Do you remember how many time slices included in this analysis?
I would say maybe 30 or so, because after you have to chop off the source part to the current and sink part, right? So I think it's probably up to 30 or so.
I see. Thank you.
Thank you. Now, let's go over to the Roper resonance. There are many facets about this. A Roper resonance is P11 is seen in the pi-n scattering at 14. Actually, the mass is really 1370. This is 1414 is just the name, and the width is about 300 MeV. It was discovered by Roper, who was a graduate student analyzing the pi nucleon partial wave analysis. The way, because in the pi-n and also the gamma-n scattering has a contamination from a delta, it's a 1230, because pi has isospin 1, also photon has isospin 1. So what Roper did is he fixed the parameter of the delta, and then look for the rest and found the Roper. By now we know it's a Bayesian approach, right? But at that time, he was a graduate student. Nobody believed him, right? Until later, when you have alpha scattering, alpha prime scattering, and then alpha is isospin 0, therefore there's no delta contamination. That's how it's confirmed. Also, more recently, that the J side decay directly into that, so that's well established as a state there. However, theoretically, there's a quandary here. First of all, when the quark model prediction, it gives the 100 or 200 MeV too high. Either non-relativistic model or relativistic model is just way too high. Even today, you cannot explain that, even from potential models. And skyrmia, on the other hand, gives us too low to begin with, but you can add sort of a 3 pi ounce coupling like to the omega that can adjust it to make it in the right positions. And there are suggestions for that pentaquark, and particularly the famous one by Jaffe and Wilczek, in association with at the time when the theta plus was a very good candidate for the pentaquark state, but theta experimentally disappeared, and theoretically lattice calculation showed that it's no such a state, and therefore the interpretation of Roper as a pentaquark is not very solid. And of course, you can consider it as a hybrid. So the more reliable things, people think, well, should be lattice calculation should be obvious. That should be a more straightforward way to calculate it. But ever since the quenched days, there's a bit a puzzle in that various groups use the different actions and find that the nucleon state as a function of pi masses are consistent. But when you come to the first excited state, they're very different. You can see that especially these experimentally remind you it's 1370, all right, it's right here. But most of the states you can see are at 2 GeV or above. Okay, and this is particularly in this case is the JLab calculation with the distillations. On the other hand, it's very strange that the overlap fermions, the purple band, will be able to get that. In other words, they used a lattice with a seek pile mass 370 MeV or so, and do a partial quenched calculation, then extrapolate. You can see this is much lower for every pile mass. So that has been there for many years. So more recently, what we tried is this. We took the JLab configurations as these are anisotropic lattice again. It's the same 24 cubed and so on. Now we took the using this so-called sequential sort of a empirical basing approach. And what we did is you fit the ground state first, and then put a prior to fix it to a certain extent, and then fit the next, and keep on going in time, and fit the next, and so on and so forth, until you reach a certain point, and using all these priors to do a global fit. All right, so that's how you get the sequential fit. But we found not a 2.2 GeV, we found that as 1.9 GeV. All right. So then the next thing is what we did is do variational calculation. Variational calc with 5 different smearing sizes, because these are radio excitations, and then we can see when the smearing size is quite small, 0.4 Fermi or so, then we got sorry, my cursor is not here. Okay, then we reproduce more or less the black one reproduces what the JLab has. But if you use the larger smearing sources, then it comes to about 1.9, closer to what the sequential method is. Okay, and this is the variational calc, and then this is Clover. Now we used overlap calculation. This turns out to be at this point. So there are two puzzles. One is the Fermi action. It looks like that the Clover is about 300 MeV higher than the overlap in this case, and also there's a 300 MeV difference when you take a small smearing or large smearing, right? So we'll now talk about the difference between overlap and Clover, which we believe is likely to be related to Carrazza symmetry, and we go down to 0.6 Fermi. Maybe the Clover, the Roper in the Clover will probably come down. But we'll talk about the smearing size dependence. Here's a test that we did is taking a wall source and the different size for the second source. Okay, this is about let me see how much is that. It's about the large size is 0.85 Fermi, the medium size is 0.63 Fermi, and small size is 0.46 Fermi. And various sinks, different sizes with we call a box smearing. You can see that the ranges as a function of pile mass. This is the nucleon. It's a different methods. You can see the ranges from 1.55, large error bars, all the way to 1.9 GeV, spread out. This is a large smearing size. You get this one, and then a medium smear size and a small smearing size. You get one all the way to 1.9. And this, I think, is really a reflection of the following features. Now, this is the one of the test for the Coulomb wave function of the nucleon excited state. This is nucleon, and the blue ones as the Roper, and there's a radio excitation has a node. But for the area function, which is a solution of linear potential, which we think, even though it's a relativistic system, if it's to some extent, if you have constituting quark masses, to some extent the potential model works, and so on. You see that the area function for the linear potential has a special features different from harmonic oscillator and a Coulomb, is that when the normalized ones for the wave function, they all start at the same height here, at different pile masses. And the node is, say, in this case is 4 point something, it's 0.9 Fermi or so. And the 3s will be look like this, something like going down. Oops, sorry. This will go down and up and so on. So the 3s, the node is somewhat closer than the 2s node. So if you take a small size smearing, that's what our speculation is. Then you project more to the 3s states. There's the 3s states is about 1.75 GeV. So you have a 1.37 GeV state and it's 1.7 GeV state here. And if you take a larger size, perhaps that's closer and then project to the 2s states. That's what we speculate that is, but it's not a completely confirmed situation. Now, so finally, we look at basin reconstruction on a 48I lattice. This is a domain wall configurations with a physical pile mass. We take the overlap as a valence and look at it, and we use different pile masses, goes 117 MeV all the way to 300 MeV. You can see that we basically see only two structures, as we've shown before. One is the nucleon, and it's around 134 MeV. You can see this is like the orange here. It's 1.55 GeV. We don't, and this is the sensitivity, of course, in the basin reconstruction, also maximize entropy. You have a state, a constant coefficient there for the asymptotic values, and we took different order of magnitude ones. You can see the sensitivity of that is really not that much. This is for the physical case. So we don't see M pi, which will just, it's all just separate issues because M pi is suppressed due to the fact that there's two particles. You have a volume squared suppression, but then you sum up with a sink, give you one over the volume. All right, M pi is one over volume square suppression, so that should be even less. Right? In any case, we don't see it, the M pi state. As people, this is relevant to the nucleon excited state contamination in the 3-point functions, which is a very important issue here. Now, but the fact that we don't really hit 1.37 GeV, and we don't see this 1.7 GeV state, is likely to be the case that really is, given our data and so on, we will not be able to resolve more states than just one peak. So it's probably the average of this peak, all right? And it will be more meaningful to see how the state will shift as a function of the smearing size. And this is for one particular smearing size, of course. All right, so, okay. So let me come to the conclusions. Of course, many physical processes involve real-time observables or energy transfer. And the inverse algorithm is being applied to all these lattices, particularly defining finite temperature and PDFs. However, the spectral decompositions in the lattice 2, 3, or 4-point functions is still a challenge. It has only limited success. We need both better data, or probably much better data, much better data, and more robust inverse algorithms. Right? That's something which we not completely successful or satisfactory. So 2 and 3-point functions can be improved because if you look at mostly the nucleon matrix element and state, and also the spectroscopy of the excited states, they can use a large basis interpolation fields. You can do variation, distillations, and so on. And however, can we put that into a challenge for the maximum entropy and NBR with the multiple correlators? Now we're working with the CalLat and get their multi-exponential approach. Turns out multiple correlators really do help because they give a different weight, even though energy is the same, but a different weight. Finally, the 4-point functions, such as neutrino scattering, is more of a challenge because the current's a local current. Right? There's no variation. You cannot put different currents. You can improve the nucleon interpolation fields to project onto the nucleon, but the current is just one current. There's no no more. So that's different. You cannot take benefits from multiple interpolation operators, right? So these are the two subjects I introduced, and that's the status as far as I know. Thank you. Appreciate it.
So thank you so much, Kefe, for this very interesting talk. It's interesting to see that in your final slide, the challenges and questions really, I think, resonated across many of the different talks and discussions that we've had this week. So
Good. I have not peeked into other talks yet.
lots of common challenges and questions.
Yes, but that's what the workshop is for. Great.
Exactly. So I see Alexander has already got his hand up. So maybe while others are preparing to ask a question, Alexander, go ahead.
So there's two things on this last slide that is, again, very interesting. And so when you have 3-point functions, usually when we have a 2-point function, we can exploit the whole range of tau values. But now you have this third operator sitting in there. So somehow it seems that challenge is even more difficult to get better data, because you're not allowed to, so to say, go too close to any of the two bounds that you have your third operator sitting in. So I guess that makes this twice as hard, at least from the data generating side.
Right. It's hard to pull them apart very far, but you can do the joint fit.
Mm-hmm.
One 3-point and 2-point function, which we are trying to talk to Calec recently. What they found, one thing which I found interesting was, we always look at the largest source sink separation, ideally 2 Fermi. Nobody has reached 2 Fermi. Where here was the 1.4 Fermi or 1.6 Fermi. It's already a struggle as you see that the data becomes bad and so on. However, what they did is they look at the way that the operator they constructed. They have a Feynman-Hellman sort of approach. So they have a very short source sink. They have all the source sink separation from small one to large ones. And what they found at the GA quantity they looked at with the joint fit 2-point, 3-point functions, and then they found that you don't really need to go to very far to get excited state contamination being controlled. And that's our hope. And that was taking the, as I said, of course you don't want to, source sink separation with a current in there, but they're trying to push them as less separated as possible and using all the data there. That's one approach. Maybe
Thanks.
That is one way to use both sort of as many data as possible. Yeah.
So I see a couple of more questions. I hope I get the order correct now. I think it's Tim and then Max. So Tim, do you want to go ahead?
So yeah, I have a short question. When you compared the elastic form factors computed in the traditional way and using the 4-point functions, can you go back to the slide, please?
Yeah, sure. I can.
So it looked like there was a difference in the uncertainties.
Yeah, right. The thing is that it turns out we use very limited data.
Okay, that's
form factor. We didn't really include. Yes, this is probably the point. There was some contention there. It could be excited state contaminations or something. There's always both of them have excited state contamination, I should say. And we use actually, you can see the 4-point function in some questions. 4-point function seems to be better than the 3-point function approach. The thing is that we didn't use all ensembles for the 3-point function.
That's fine. I thought it might be. Okay, thanks.
Yeah, this is proceeding work, but we're not getting the more. You should get a fair comparison with the same statistics.
Thanks.
Yeah, people. Well, you have a good eye. Many people catch that. Some 4-point functions better than 3-point functions.
Max, I think you're up next.
Yes, thanks. Hi, Cafe. Thank you for the nice talk.
Good to see you.
Yes, I just wanted to make a comment about the excited state looking for the roper. So I just think it's good to keep in mind that, of course, really we have a spectrum of finite volume excited states, which is very complicated, including both NPi and NPi-pi-like states.
Yes.
So I think it's very hard to say what our expectations should be for these kinds of analysis. It's not so clear that we'll see a simple state that we can associate to the roper.
Yes. I understand. I fully understand. People have a lot of very sophisticated technology of doing the scattering states, but here we're looking at some just different aspects of it. First of all, the roper is not very broad. It's 50 MeV widths, and furthermore, when you look at the scattering states, it will be a mixture of the roper and NPi state. Let's say take NPi, right? And of course, when you vary the volume and so on, the states will tend to repel. The states will repel each other. But from the case that they start to repel and then mixed and not cross over, go over, it will be the range of order of 100 MeV or so. So we're looking for a state at this point, roughly within uncertainty of 100 MeV or 150 MeV. But compared to the case, for example, so we're not really for precision for the pulse at the stage. We're looking for a state, and that so avoid using roper resonance as a state. You can see we're trying to. The initial state is resolve the difference between a 2.2 GeV and a 1.6 GeV, 600 MeV difference. Right? So that, of course, eventually when you want to do it right, as you pointed out, one should use this NPi scattering and NPi-pi even to see whether that will shift, but I doubt that will shift the widths very much. Actually, we looked in the paper that we wrote, we look at the row was a pi-pi scattering. You look where the row is. I mean, before the pi-pi mixed, because they're far away. Either volume is very small and so on. Then the row is here, and the pi-pi is either here or somewhere there. When they start to mix, and you look at the row is basically more or less constant. It's in between. In other words, when you shift both of the row state, eventually the resonance state will be somewhere in between. So it's not really. Look at the JLab data and George Washington data, you find the unmixed state, and eventually the resonance state is basically very close to each other. And so is we would take that, and maybe it's an estimate of what that is. It's not really.
Yeah, I would have some other questions and comments, but we should probably take it offline. I think it would take too long.
Yeah. Well, certainly Max and also Kefe, if you can stay during the coffee break, then the Zoom session will stay open and we can continue this discussion perhaps then. Sure. I do see Harvey has a question, so maybe Harvey, you might like to ask.
Yeah. Hi, Kefe.
Yeah. Hi.
I was wondering if you had tried first subtracting the elastic contribution before applying the backwards-Gilbert method.
Right. Very good question. Actually, that's what we did. I forgot to mention. I forgot the one that before. Yeah, this is one this is one I didn't mention. We subtracted the elastic state to get the other states out. Sorry, this one. Yeah, sorry. We really subtracted the ground state, the elastic scattering, to get the next state there. That's what we did already for the transfers. Yeah.
Thanks. Thanks, Harvey. I see Nazario has a quick question in the chat. I think it refers back to the to the roper plot. I guess Nazario. So he's asking if the different points on this figure correspond to roughly the same volume.
Yes, the answer is the same. We used. Let me see if I can go back. No. Oh, that's the right. Yes, the volume for this. I think this is 24 cube clover with a 0.12 Fermi, and this is the 24 cube domain wall with a 0.114 Fermi. So it's basically the same. This is the 400 something MeV. Pi mass is 390 or so. So these two cases, the overlap, and the others, these are clover ones, are very close in volume and biomass.
Thank you. Thanks so much, Kefe. I think this is probably a discussion that might continue during coffee.
Good.
So maybe we can thank Kefe just now for a really very nice and stimulating talk. So thanks so much, Kefe.
Thank you.
And we will move to the next talk. So we're switching gears a little bit, staying with nucleons, but now our next speaker is Stefano Carrazza, and he's going to discuss how we can tackle this, calculations of proton content, but now on a quantum computer. So
yeah.
You're pushing us out of our comfort zone, perhaps a little bit, Stefano, but I'm looking forward to it.
Yeah. Can you hear me, right?
Yes, perfectly. Thank you.
Can you see also my slides, right?
And we can see your slides perfectly. Yes.
Yeah. So thank you very much for the invitation. And indeed, I'm today trying to push towards the frontier of quantum computing. As you know, this topic is getting more and more hype in the last years. So let me try to give you an overview of what are the possibilities today and why are we looking at this technology. You know? Just to give you a background, I am a particle physicist. I have been working for many years in the determination of PDFs using LHC data. So I'm a member of the NN-PDF collaboration. And when we start looking at quantum computing, we consider the possibility to improve methodology. Now that's the main motivation. Now, in terms of introduction, I like to show this slide where I summarize, let's say, what I believe that we are moving in terms of technological development. So we have been using computers in terms of general purpose devices for many years. So we started from CPUs, and nowadays we are moving towards application specific. So we are using GPUs, graphical processing units, for machine learning, for Monte Carlo simulation. And then we are also considering new architectures like FPGAs, and why not maybe in future quantum chips. So we are getting more and more application specific, you know, and this is something interesting, but at some time in parallel requires a lot of investigation. In terms of quantum technologies and quantum research, the last 10 years, we have observed a lot of development in the different branches, from quantum communication to quantum computation, simulation, and sensing. So these are the four branches which are improving and trying to get, let's say, grants and research projects involving these technologies. And here below you see the evolution in terms of experiments from 1988 until, let's say, a couple of years ago. You see the growing number of qubits that the different labs achieved in different contexts, and we're using different technologies. So we are growing. So the question is, can we find real-world applications that could improve our life, could improve our research topic, for example? Now, in 2019, Google has published in Nature a paper where they claim the quantum advantage, or if you wish, say, first indications that we could achieve quantum supremacy by constructing a system with 53 qubits and proving that the system was not able, you could not reproduce the calculation of the system in a classical supercomputer. No. And this was, let's say, the first time we see such kind of a benchmark. You know. Obviously, if you look into details, you find that the kind of calculations they are doing are based on the sampling of pseudo-random quantum circuits. This particular choice is probably not very appealing today in terms of applications. But anyway, it's interesting to see that we could achieve something impossible in a classical supercomputer. So given that we have all this hype, obviously we can have a look at the landscape of players. And today there are many people from companies, from research centers, and even grants now that are trying to push towards the development of these techniques and technologies. So you can find almost everything, from companies selling computing hours, from researchers trying to figure out the best models that achieve some results. So this is something really interesting to see. So there is some sort of synergy between the different worlds. However, being very realistic, now the question is, what can we do today with these tools? So where we are, in a few words. And using a Presque phrase, we can say that we are in the noisy intermediate scale quantum era. And we are trying to, let's say, what we can do is develop new algorithms. So try to take the current quantum computing frameworks and understand what are the possibilities. And the second point that you see here is the possibility to take our problem and convert this problem into quantum hardware. These are the two ideas. Now, both of them are quite challenging, in particular because we have noise, and the experiments are quite noisy in general. So in terms of algorithms, we can try applications using the gate model, which is something very, very old now, but it's probably one of the best quantum computation models because it's reversible. On the other hand, we could look at variational approaches. So the variational approach considers a quantum system as a model with parameters. So you could use the hardware as a model. And finally, the third block, annealing, which is probably one of the most interesting applications in quantum computing today. So performing adiabatic evolution, so trying to prepare a system and observe its time evolution, and then extracting extra informations, minimize problems, discover the ground state of Hamiltonian. So this is quite clear now in terms of results. So these are the three branches that we can start investigating. However, we still have many problems. So the first problem is that we don't have devices. Now the devices are very limited. We have a limited access to these devices. So we still rely a lot on simulation. And simulation is performed on classical hardware. And we have several constraints from memory to number of nodes. So the computation is quite challenging. On the other hand, we still have open questions concerning the optimization of quantum calculations on real devices. So questions like control and reconstruction of measurements is something that's still in research. We have to optimize that. And don't speak about the infrastructure. When talking about how to access all these objects and how to operate them, this is still very primitive in the current moment. Okay, so you can, and now let me just make a small break from this introduction and talk about why I'm involved in this game. Now, as you can see, we talked about simulation, network, algorithms, control. So we're talking about software development that requires the knowledge of the different pieces. And this particular software, when we have a quantum project, it's called quantum middleware. It's the full stack that will manage this, different things, but we'll try to glue together the different blocks. And this is quite important. So the middleware is something that will allow us to do some physics, do some research. And in particular, I have been working on this library called Kibo. So Kibo is an open source full stack API for simulation and, more importantly, for hardware control. So you define a language which allows you to code, to write down your algorithms. Then you could, and as we are doing, store this algorithm. You store algorithms and models based on this language. deploy tutorials and examples based on different papers that have been released from different fields. And finally, the most important tool that I believe is relevant for this project is the laboratory tool. So today, if you look around, it's very hard to find a piece of code that we allow experiments and laboratories to plug their hardware and automatically start operating. So that was the original idea, to have something very simple and flexible to accommodate multiple applications and to provide to the laboratories the required tools in order to achieve very fast development and get the system working. So that's why I'm presenting here, because thanks to Kibo, we managed to do the PDF determination, and we're also doing other projects involving some of you that are here today. So to give you just a more clear picture, there are two paradigms that are supported by this language. So the quantum circuits and the quantum annealing. And you can find pre-coded models with primitives for both approaches. So the development for this branch is very simple. So you just take the primitives and implement for your specific application. But from this point of view, at least you can. And then the nice feature of a framework, a middleware framework, is the possibility to be completely agnostic. So if you write your project using this framework, then you can execute it on classical hardware simulation or on quantum hardware, and you don't have to change almost anything in terms of programming. So you just decide where you want the deployment, and then automatically you get the results. So finally, going back to the backend. So today we have 4 simulators and 1 quantum hardware. And for the project that I will show now in the next slides, so for the part on distribution functions, we have used the Kibo ThetaF and the TensorFlow backends for the simulation. So this allows us to take the quantum simulation and plug into the current frameworks that we use for PDF determination. And this list we will expand in the next months and years. Okay, so now that I explained you a little bit, so introduction and coding, how you achieve, how you can go through these different topics. Let's talk about the quantum models for PDFs. As we saw in the previous presentations, there are many ways to perform PDF extraction, PDF determination. I have been involved in PDFs using data, real data, so latency data, DIS, fixed target dialing from the past 20, 30 years of experimental measurements. And from this perspective, the target of achieving and obtaining PDF, so the blue functions that you see here on the right, consists in fitting data. So you have to fit your data by computing a matrix element, so a theory component that I call here X, which is in convolution with the PDFs. So if you manage to perform an acceptable fit by looking at statistical estimators, by performing cross-validation, then you might get distributions, partonic distributions, as you see in these 2 plots, with uncertainty bands. Now, and the choice of the specific methodology, so how can we do, what is the regression model, what is the technique, this depends a lot on the collaboration that is working on this specific topic. For example, in my case, I have been working in NNPDF, so we have been using neural networks for the parameterization of PDFs to avoid possible bias due to polynomial choices, instead of using Chebyshev polynomials or whatever other functional form that has a fixed layout. And we have been using that into a framework in a global fit setup. So we have more than 6,000 data points from different experiments. So you perform the fit and you get the results. So from our perspective, the question is, can we replace neural networks with a quantum model? So can we use a quantum computer as a nonlinear model? And this question is really strongly correlated to what we are doing. So in artificial intelligence, we have at least these 3 major techniques: supervised learning, and supervised learning, and reinforcement learning. So in this, the common feature of these three learning paradigms is the fact that we have a mathematical model with 3 parameters that you have to tune, and these models are able to predict something. So keeping this in mind, we have had a look at the quantum models, and we found these variational quantum circuits. So circuits where we have the possibility to optimize and determine the best parameters for our model. So this is what we do. So variational quantum circuits, and the rationale for variational quantum circuits is very, very simple. So suppose you are in a Hilbert space in an initial state position that I'm showing here with this yellow star, and I would like to move on and find the optimal solution for a specific optimization problem. So here I represent it with this red rectangle square in particular. The question is, can I find a pattern in this space that allows me to be very, very close to the optimal solution? And from a practical perspective, the answer is, in principle, yes. And we can do it by creating unitary gates or unitary operators that can be applied to your initial state and can slowly go down to the optimal solution. That's interesting because by applying unitary gates, we have a reversible, let's say, a reversible computing paradigm. So that's pretty interesting. So we can go and change direction. And on the other hand, we could parameterize the operators in such a way that we can vary and see if our variations are bringing to the solution, to the optimal solution. Now, this is the idea. However, but we would like to have something a little bit stronger, no? Because of the dice, you can argue that the number of operations, the number of unitaries would be extremely large, and then impossible to achieve the optimal solution. And that's the good point. The positive feedback from this idea is that there is a theorem, the soluble ThetaF theorem, which states that if we had a set of dense unitaries, Ui, that I represent here, and we have the circuit approximation V that connects the initial solution, the initial state, to the optimal solution. If we define an error, delta, then it's possible to find a product of unitary gates from this set of unitaries that approximates and is very close to the optimal solution. So the distance between our dense set of unitaries and V is very, very tiny. And the theorem also tells us that in approximation, the number of unitaries required to achieve such target optimization is order logarithm of C, and where C is smaller than 4. So, in conclusion, we can perform this operation, and the number of gates is not infinite. So we can manage to get a finite number of gates that allows us to achieve this level of uncertainty, now that desired level of uncertainty. So that's the idea, and that's why we are here and trying to check if this theorem and all these variation approaches are acceptable for some real application. So how can we do it? Well, we could define a system with multiple qubits. So here I'm showing different qubit lines. Create a unitary gate with arbitrary parameters, theta and x in this case, because we're talking about PDFs. And we could select a random set of parameters, then perform measurements, project the measurements into a loss function, and optimize that loss function using a classical optimizer. So the classical optimizer will try to select a best set of parameters that will minimize the loss function. So in some sort, this is a hybrid architecture, classical quantum architecture, where the quantum chip or the quantum simulator is the model, is the nonlinear model predicting outputs, while the classical counterpart performs the optimization. So everything that concerns computation of gradients, finding the pattern to achieve the minimum is delegated to the classical computing. So it's a hybrid approach which is feasible and we can test. So that's quite nice. If you're familiar with machine learning, you can imagine that in normal, the standard processing, you have the inputs from the architecture. In our case, in PDFs, the only input is X, so the momentum fraction. And then the neural network will be evaluated and you get the PDF as an output. So this is the standard approach, forward pass to get the validation. In the quantum approach, we change this idea. We can fix the input. So you have an initial state, which can be the vacuum state, in the case, the 0 state. And then the inputs are injected inside each unitary gate. So you see the two inputs that are inserted inside the different gates. So this is something different from the standard machine learning approach. But it is a technique that allows us to test and to introduce non-linearities during the model training. More specifically, then we can ask ourselves, what's the aim? Why we're doing this? And I can at least say two to three ideas. And the first is the proof of concept. So we're trying to study a new architecture at the end of the day. Is a new machine learning or quantum machine learning architecture that will give us the flexibility to verify if the non-linearities from a quantum system are more powerful than classical machine learning applications. So this is the first curiosity. The second and third curiosities are related. So it's the fact that we are building a device that can hold a model. So we can deploy that model on a specific hardware. And this is quite interesting because it's similar to what people have been doing with FPGAs. Now you can store the model there and then take advantage of the memory, of the speed and the power consumption of these devices. So it's almost that are the most important or relevant points for this discussion. However, we are in the NISQ era, so everything that we will do is really dominated by uncertainties and by the quantum device the coherence, errors, T1s and T2s. So that's really challenging to do. So how can we build a quantum PDF model? We prefer to do it in 3 steps. So in the first step, we take a PDF that we already know and try to see if we could define a quantum model that approximates this input PDF set. So this is what I call stage 1. It's a very simple operative approach, but we can test it until reaching a good level of accuracy. And then we have stage 2, where we take the quantum model after training in a simulator and deploy it on quantum hardware and check the difference and check how this new model performs in a real-world machine. So this is something optional today, but we can do and still check what are the advantages and problems that may raise from that. And as a stage 3, we can bring everything together and perform a full fit. So you can consider the quantum hardware as your model and then perform the hybrid classical optimization directly using data and the quantum computer for the model. So what we do is we define a circuit. So we take a parametric unitary for a specific number of qubits. We are associating each qubit to a PDF flavor. And here we have a very, very open set of possibilities to define a PDF. So in our particular setup, we decided to take the Pauli Z operator and then project the measurements on top of that and define the PDF as this ratio between the measurements, the ZI, in such a way that the output of the quantum PDFs is something unbounded. So there's no upper limit or lower limit, and you can get something very similar to a linear layer in a neural network. So that's one possibility. You can test many others. Then the second important step is to define the ansatz for the quantum model. And here we decided to apply, to define a layer. This is the definition of a layer, where there will be many unitaries, or at least a first layer of unitaries, and just after controlled rotation. So these are rotations that we perform over the different qubits, but there is a target and a controlled qubit, and this will create entanglement. Okay, and the entanglement will probably, so the question is if the entanglement could improve or could accelerate the convergence of this model. So that's the kind of architectures many people have been trying in other contexts. So we decided to take it and to build finally a model, a complete model, where we attach different layers, and at the last layer we perform measurements. So that's the standard architecture that we can. Now the question, still the open question, is what can we use as a set of standard unitaries for the different layers? And here again is a question of some heuristics and tests, and we have decided to take two different ansatz, the weighted ansatz, where the unitaries are parametric. They rely on a set of coefficients alpha and our PDF momentum fraction x. And then, as you can see, in this case, we multiply two rotations, one over z, another over y. And the arguments of the different rotations are the products between our coefficients. So these are the parameters, the alpha 3, alpha 4, alpha 1, and alpha 2 are the parameters that the optimizer will have to find during the optimization, while the x is the momentum fraction that we request when performing the PDF prediction. So we introduce these parameters. The rotations are exponential, so we are generating a non-linear model at the end of the day. So this is the weighted. The Fourier ansatz, on the other hand, is quite similar, but we are introducing even more rotations. So we have here rotations of z, y, and we have some scaling factors. So in principle, by defining both ansatz, we should have enough flexibility to cover the full space of rotations in the block sphere. So presumably get the maximum flexibility when optimizing the problem. So now moving to stage one, what we do is that we, in this plot, you see the first column, the single flavor PDFs for the glue one, up and strange. In gray, we use the NNPDF 3.1, so it's a classical fit using neural networks and LHC data. But then we try to build the circuit, the quantum circuit, and fit, and just doing classical fit. And as you can see, the orange curve and the blue curve, which are respectively the weighted and the Fourier ansatz, they are working pretty well. So you can see that they cover the central values really, really well. If you do single flavor, you get it quite well. Now you can also create larger circuits where the different qubit lines, they represent different flavors. And then again, you repeat the exercise. And also in this case, you see that the level of agreement between the input PDF and the fitted quantum model is pretty good. On these tables, you can see the chi-square between the original PDF points and the quantum model points as we increase the number of layers in our quantum model. So if you have a model with just one layer, so 32 parameters, the chi-square is pretty bad. But then as soon as we increase the number of layers, the chi-square drops and becomes really quite good. And it's very nice to see that the number of parameters is reasonably small. So we are talking about 160 to 120, depending on the level of accuracy. And these numbers are quite competitive if you look at the neural network original size. Now, neural network that we are using today in our fits can quickly go to 300, 400 parameters to get a similar level of accuracy. So that's something positive. At least you can say that there is some place for these devices in terms of flexibility. So entanglement might help in the optimization. After doing that, so you can perform a multi-flavor fit from a simulation point of view, and this is the kind of output you get. So you can get for all the 8 flavors a quite good agreement between the original PDF and the quantum model. So that's really quite reassuring. So now, given that we have a model, we can go ahead and try to perform a global fit. So we have the model, we have the architecture of this model. So we can take all the framework and the software we have released from NNPDF and this open source, and go ahead, plug the quantum model for the PDF parameterization, and then perform the optimization. By doing so, here we have some output results. So in green is the quantum PDF model using LHC data, using the full global data set of data points, compared to the NNPDF 3.1 in orange. So here we have the down quark, gluon, and up quark. For all these flavors and also the other flavors that I'm not showing, the level of accuracy and the quality is pretty good. So we achieve very similar behavior even by fitting directly data. Moreover, if you compare theoretical predictions, so if you take Atlas Jets or CMS or any other model, also here, both sets are really very similar. So the quantum model is doing exactly the same job as a neural network approach. And finally, correlations, which are quite important. So you can take PDF correlations from the NNPDF 3.1 and the quantum PDFs, and you see that they are in overall quite similar, and including the phenomenology. So computing candle cross sections for example, the Higgs production, you see that the difference from NNPDF 3.1 and the quantum PDFs are within the uncertainty band. So that's really remarkable in terms of application. Now, okay, this is the good news of the approach. Now the bad news is what happens if I take the final model and deploy it on a quantum hardware. So the stage 3. So we tried this exercise. We decided to convert and to deploy our model in the IBM Atoms system. And here you see the results. So the green points that you see are the measurements performed by this IBM system using the single flavor model. So each flavor has its own model, and we perform the query independently from each other. So you get the maximum accuracy and the smallest circuit for each sample. But in overall, you see that you can reproduce it within 1 to 2 sigma, depending which flavor it is, but we lose a lot. So we lose a lot of accuracy when deploying on the current hardware. Even if you do more than 8K shots per point, there is still lots of fluctuations. And the second curiosity that we try to answer is what happens if we try to predict flavors together, and we see that the quality is pretty bad. So it's still very far from the original model. So here the red lines are the simulated noise from Melbourne, which is the largest system. And that this can be improved just by reducing the theoretical noise uncertainties that are available. So if you started reducing it by 10% or 5% of the nominal value, you might improve it and get something closer to the desired distribution. But still today, very, very early, so we cannot use that for production, let's say. But yeah, that's, say, an investigation, and you can at least confirm that quantum model using variational circuits is able to produce the level of flexibility required by, for example, a regression problem like PDF determination. Yeah, so I achieved at this point I'm in my outlook. So you saw 2 different things, in particular the framework for fitting that I presented, so Kibo plus the variational approaches. And I hope that these kind of applications could at some point get more and more say sophisticated in terms of error, in such a way that we can at least consider quantum devices in a different way. So it's not only to achieve computations that we are not able to do today or that are involving quantum mechanics, but rather take advantage of entanglement superposition when doing variational optimizations. and classical hybrid quantum algorithms. So thank you very much.
Thank you so much, Stefano. That was fascinating. So thank you very much. I can open the floor to questions if there are questions. Alexander, fire away.
Hi, Stefano. Thanks for the interesting presentation. I would like to better understand where the benefit of the quantum representation is. So if I understand correctly, instead of using a neural network where you act with non-linear functions on real numbers, you're now expressing the mapping of x to f to PDF of x using quantum operations. And it seems that this allows you then to find the optimal configuration using a quantum algorithm, and that should be in theory faster, for example, than what you can do with non-convex minimization with the classical numbers. But is that really the bottleneck of current neural networks? That
No, yeah, you're right. So we're not claiming that the quantum computer, the quantum machine learning approach is better, faster than whatever.
Okay.
Classical. So the classical is still the state of the art now today. But the open questions that we had is can we take a quantum model, and if we put the number of parameters from this quantum model versus the equivalent neural network, do we have the same type of flexibility or a little bit more? That's something that we try to check here, and you see that there are some assumptions, and by looking, for example, at this table, you see that with a limited amount of parameters, you still do a really good job, I would say. So there are some place for improvement, and for sure in the next years with the technology, in the experiments in particular, you could achieve better results. But just another comment is concerning this particular paper. Now, here we did simulation, and the simulation takes a long time to converge. So if we had to replace neural networks with the quantum simulation, then that will be completely unfeasible. So today, a fit takes today, a global fit takes 1 hour with neural networks. While here, we have strong limitations of memory and multiprocessing. We need more than 20 hours for a single fit simulation. But maybe in future, if you have a hardware, and this hardware is extremely efficient and fast, then why not? We could imagine as a sort of GPUs for machine learning. Maybe this will be the idea.
Thank you.
Thank you.
So I don't see any other hands up at the moment. So I might just quickly ask Stefano, I probably missed, but how many qubits did you use when you deployed on the test on the actual quantum hardware?
Yeah. So we try to do two approaches. So the single flavor uses a single qubit.
Okay.
So you take just the output from it and you project it into using the projections for the Z pod. And then for this particular setup, we tried the IBM Atoms, which is a tiny machine.
Mm-hmm.
But instead of using, I think the Atoms has 5 qubits, but instead of using all the 5, we decided just to pick up a single qubit. The one with lowest, the best quality is T1 and T2, and that's what we get.
And is there a significant qubit overhead for error correcting, or how do you handle that?
Yeah, in principle, you should do that. So if it's possible, you should try to apply as much as possible error correction. The problem is that well, we decided just to measure the difference and see where we are, because as we discussing with the question from Alexander, all these operations will increase the amount of post-processing, and then all this game will become completely useless. So this investigation, I hope that the new technologies, maybe trapped ions, might accelerate and improve this situation.
Mm-hmm. Great, thank you. So I don't see further questions, so maybe we can thank Stefano again for a really fascinating talk. It's really interesting to see how this works in practice for real quantities. So thank you so much.